So if we can recall from Unit 3, we can differentiate log x. The differentiation of log x creates 1 over x. Now I'm hoping you've seen that currently. I'm hoping you've gotten that far in Unit 3 because I do think most schools you start Year 12 the year before a little bit. You do a little bit of content the year before. So yeah, if we derive, usually you'd say ln x is usually what they use. If you derive ln x, you get 1 over x. If you derive ln fx, you get the differential of fx over fx. And that's also down here. So then you can do the opposite by deriving. Now this should probably have a plus c here. They've forgotten the plus c in these examples. You can never really forget the plus c. So these are our general formulas, similar to our last page. These are just our general formulas that if you understand them, you will benefit. Now this is the similar example of we have a linear function inside of the log, and then it will end up looking like this. Looks very, very similar to how this is generated, because it is very similar. The most general use formula though, the one that aids us the most, the one that we can basically take anywhere we want, the one that encapsulates this one here and this one here, is this bottom one. So the integral of the differentiation of fx over fx is log fx, or ln fx is usually what we use, plus c. So if you can remember this one, this will encapsulate everything, and that's the best one to remember. So let's do an example. Okay, so we're going to do the definite integral of 1 over x, sorry. So now we can apply our knowledge of our formula. We know that if we did derive ln x, it would be equal to 1 over x. So that means in these square brackets, we're going to have necessarily lx there. We have e to the power of x, or e to the power of 2. I don't know why I wrote x. That would be a very hard thing to solve. And then we have e down the bottom as well. Okay. So this becomes ln e squared minus ln e. That becomes 2 ln e minus ln e, which becomes 2 minus 1, which equals to 1. And that's just using our logarithmic rules. If we have a log base b and then it has b inside of it, that is equal to 1. And ln is equal to log base e. So we have ln with an e inside of it, that is equal to 1. So now there's a more complicated one. This looks like a linear function is inside of our log here. So we're going to do a definite integral over this here. Now we could just check a log. We could say, okay, what if we derived ln 2x plus 1? What does that create? If we derive this, that would derive down to, might want to put it in a place where we have a lot more space. If we did have ln 2x plus 1, that would derive down to 2 times 1 over 2x plus 1. Because remember, the differential of what's in here goes on the top. And then what's in here also goes on the bottom. So that means at that point that we look very similar to this. The only difference with this is there should be a 2 on the top, and that's sort of what we're missing on this side here. So we could assume, okay, so we must have a constant value of 1 over 2 getting multiplied by this, 2x plus 1. So we can take our 1 over 2 out the front. Oopsie. 2x plus 1. And now we're looking like we're in the right form. So we can utilize this logarithm that we hypothesized would be related. And we can't forget our 1/2 as well. 1 to 0. So that means we have 1 over 2 ln 2 plus 1 minus 1 over 2 ln 1, because our 2x becomes 0. So we could just put 1 over 2 outside at the front of everything, and we say ln 3 minus ln 1 is equal to 1 over 2 ln 3 over 1, which is equal to 1 over 2 ln 3, if I haven't made any mistakes. Yep, okay. And this over here is just using our logarithmic rules. I know that if ln whatever subtracts ln whatever, then that is equal to ln, let's say ln a subtracts ln b, that is equal to ln a over b. And that's just one of our rules that you should probably get comfortable with if you don't know it already. Okay, so we have another example here. We're going to, okay, yep. We're going to find what is fx if we know that the differential is equal to this. So let's utilize that. We're not doing a definite integral, we're doing an indefinite integral, but we know this point here, so we can actually find what c is utilizing this point. Find that c is one true value, instead of it just representing a whole bunch of possible values and an infinite amount of possible functions. There's only one function for which this is true and for which f1 is equal to 0, because we're going to have one c value. Okay, so let's prove this. Let's utilize this. So we're going to get the indefinite integral of 3 over 4x minus 1. Now, if I were to look at what would the let's say fx did equal ln 4x minus 1, then the differential of fx would actually have to equal 4 over 4x minus 1, and instead we have 3 over 4x minus 1. So I'm going to assume that there was actually a multiplies a coefficient of 3 over 4 there, so that 3 ends out on top. So if I were to derive this, you would see why this would make sense. Equals 4 over 4x minus 1 multiplied by 3 over 4, which is equal to 3 over 4x minus 1. If you find sort of this difficult just to look at it and then interpret what coefficient was there, then do just memorize and utilize these formulas. It's sort of just a personal way that you can choose to do it. Do you want to basically just memorize the formula, memorize how I turn this into that, or do you want to have sort of a different type of intuitive understanding as to how you can basically reverse engineer what you're looking for? So I know that this is equal to ln, or we'll put the coefficient out the front, 3 over 4 ln 4x minus 1 plus c. Now, so we've basically found what it's equal to, but we just don't know what this plus c is equal to, unless we choose to substitute in values, because we can substitute a value in. We have, when we substitute 1 into all values of x, oops, that's a little mistake there. When we substitute 1 into all values of x, then we know that the result is 0. So we can say 0 is equal to 3 over 4 ln minus 1 plus c. Now, that's a terrible mistake. I was very confused for a second. 4 times 1 minus 1 plus c. Sorry about that. So now it's 0 equals 3 over 4 ln 3 plus c. So now c is equal to minus 3 over 4 ln 3. So that means we can substitute that into our function, and then we have our final function. So we can say y, or in this scenario, it's probably better to write fx, because that's what it's asking for. It wants you to find fx. Fx is equal to 3 over 4 ln 4x minus 1 plus or minus 3 over 4 ln 3. They both have a coefficient of 3 over 4, so I can do my logarithmic subtraction. So that becomes 3 over 4 ln 4x minus 1 over 3. And that's probably should be our final answer, unless I made some little error. They don't actually bother even trying to solve it any further. I think the last step would be to create a 3 over 4 ln, and then use your logarithmic subtraction to figure out what the answer is there. So basically, to summarize this sort of problem, what this is telling you to find an indefinite integral, and then to be able to substitute one value in to find what is the line that fits with that. So we found the indefinite integral, which has the plus c on it. So that's not a specific function. That's just a bunch of different functions, because there's any possible value of c. If c was 1, if c was pi, if c was 1 million, it would create a different function. But by substituting in the values, since there's only one c, we can find that there's one possible value of c for which f1 is equal to 0. So we were able to do that, and that allowed us to find an actual single fx that exists, for which this is the integral, for which this is the differentiated value, and for which the line goes over this point.